Hey, what's up, YouTube? So here we are back again, Optimal Start Math Playground. So right now we have done model 0, just a linear model. We did the model 1, which is pretty complicated in my opinion. Just doing the nonlinear as the delta temperature between zone temperature and occupied zone set point grows, and now model 2. I thought that these models would get more complicated as it's getting into here. Also, this one and this one is not part of the PNNL paper that this is based off of. But I have been, since we covered this one, learned a bunch, going to model 2, I find that it is really similar to this. It's model 0 with kind of a little bit more of a twist to it. So I thought it might even be kind of cool to maybe even enhance the Vibe Coder repo, the model 0. It's basically the same thing as the linear model with a degree per minute, but it's actually factoring in outside air temperature as like a ratio to add on some extra minutes. So it's kind of interesting. So yeah, let's get into it. I also would highly recommend for people out there the PNNL paper. Hopefully the PNNL does not care that I get pushed to their paper, but I think it's so good. There is so much interesting stuff in here, and I've been trying to soak the content in for about a year now, and I haven't read it for a couple months, but I'm rereading it again. So we're talking about resistance, capacitance model, more of like mechanical engineering, upper graduate level academia, a lot of the math equations, and model 1, which we did already. So this is kind of like a little bit of the nuts and bolts, getting into model 2, which we'll talk about in a little bit. But so yeah, we're just outputting minutes, and it's so the paper goes into like a lot of more details, and basically the lots of charts on the best performances between these different models, and they tested it out on heat pumps. So I found it kind of interesting that the Model 1 is most effective on like interior zones of a building that don't have like exterior walls, which makes sense because it's not factoring in outside air temperature. Obviously, the ways that you calculate savings, just you're not running the equipment or compressors. Savings for each model. In Model 3, which we haven't gotten to yet, was the winner, even though that I think Model 1 is kind of the second runner-up, but it's not by much. Like this, it's not like drastically huge differences either that I can get out of this. So where are we? Load more pages. Just want to show you guys this. It might be, there's just so much to so much in here. Yeah, just like predictions of Model 1 were worse than Model 2 when dealing with large increases of zone temperature during optimal start, which is the difference between zone temperature and zone set point. When the increments were bigger, however, Model 1 behaved better. So they have like a bunch of notes in here. Some of the models performed better in different scenarios, but overall, Model 3 exhibited slightly superior accuracy. And they also talk a little bit of this, latest and greatest research. If it's an office building where the building sits unoccupied over the weekend, Monday morning is still an issue that the latest and greatest math models haven't solved yet, just because that thermal mass, stores and releases, a lot of energy. So it's just more time required to condition the space on a Monday, which in maintenance, which building operators, maintenance intuitively operate schedules a lot longer on Monday mornings, just by their best guess. Okay, so let's get into it. Let's see. I might even try and do a couple days in a row if time permits. Okay, so we should be on day 14, model 0 versus model 1. Actually, I think that, we're on day, actually, hold up. I think we're on, which day are we on again? I think we're on day 21. Model 2 versus Model 1. So, yeah, this is where we're at. Okay, so Model 2. So, Model 1 assumes indoor conditions dominate and is best for interior and high mass zones. Model 2 adds weather correction and is better for perimeter zones with outdoor fluctuations, which definitely happens. Perimeter zones are usually worst case scenarios. Review of your own buildings, where would each model work well? Consider insulation, blah, blah, blah. So here we are on model 1 and 2 predictions for the same zone. This makes me just kind of interested in checking something real quick. I know Model 1 kind of talks quite a bit about best for interior zones with high with a high amount of thermal mass. So I might actually, this is the one we finished yesterday, so this is our Model 2, but I might try and cover this all in one day because it's very similar to our first week. Okay, so day 15, why indoor temperature isn't enough. The perimeter zone exposes to weather. Indoor temperature alone doesn't capture how quickly a space will warm due to that part of the paper that we talked about Monday morning issue, thermal mass, different kinds of properties of building types like concrete versus wood. Cold air, outdoor air can continue to steal heat during warm-up and slowing the process. Model 2 introduces outside air temperature to account for this effect. So this is basically it. This is our delta temperature, the base rate in our degree per minute, kind of the same thing that we've been doing in the Model 0. And then here we are in the temperature base, the delta temp, and base rate. So this is a ratio here that basically is the nuts and bolts of Model 2. So let's just run this code. So right now, here's Model 0 tutorial, Model 1 tutorial, how we have the same data. And I'm just going to start on Model 2 tutorial. Code base, a little bit of Python. Then we can do Python Model 2 tutorial. Not using this yet, but maybe we can in a little bit. So demonstrate how colder air increases the predicted time. So what do we got here? We have a diff. So this must be, diff is the drop in outside air temperature compared to yesterday. So they're pretending that there would be outside air temperature included, because this historical data doesn't do anything with outside air temperature. It was only degrees and then minutes. And then if we wanted to use this enhanced data structure, we would also have to have another point here for outside air temperature that's recorded at the time that these two variables are recorded. So like when we execute the algorithm before the building starts, that is when we record our zone temperature and set point deviation. Minutes is the amount of minutes it takes, and then we would also record outside air temperature at that given moment. So this would be calculating the difference in outside air temperature compared to yesterday and computing a ratio, which is used to add some extra minutes to the final product, which is a little bit goes beyond model 0. So model 0 was just computing an exponential moving average across these different. So we're just taking an exponential moving average across this and then computing it degrees per minute and then outputting minutes from that model. And then this model 2 we'll get into factoring outside air temperature, kind of doing the same thing as model 1, I think. Okay, so what do we got here? Explain why colder outside air temperature conditions result in a ratio greater than 1. What happens if today's temperature is warmer than yesterday? Which interior perimeter zones would benefit from? So we talked about that. This is zones in the building automation system, the building, where if you have multiple exterior walls, those are best, may benefit the most from this model. Sometimes I can remember in like an air handling unit system that cycles at night to maintain heat in the space. Sometimes I would, when I would set up building automation, is pick the worst case zone to wake up the air handler in the middle of the night for night heat cycling purposes. So kind of similar. Explain why outside air temperature results in greater ratio of 1, value of 1. So I think what they're getting at with this is, so if we put a value of 10 in here, see how our ratio goes down. So if I think we'll get into like tuning some parameters in here, but so if our outside air temperature is warm, we don't need to be cycling the heat on, I guess. If the outside air temperature is warm, a ratio less than 1 would subtract minutes. And then if our ratio is greater than 1, we will be adding more minutes to our model, our minute calculation, or whatever. So that is kind of the nuts and bolts of it. I think I'm going to go move on to the next one. So we're just pretending there's this one day of data and many different outside air temperatures in that. So if I go to day 16, Model 2 uses a reference for outside air temperature according to the PNNL paper. Tref is set to 0, 32 degrees for heating, and 37 degrees C, 100 degree F for cooling. Tref represents a worst case condition where the equipment must run continuously. I guess. So if it's 100 degrees outside, should the air handling unit run all the time? Maybe. The ratio is calculated Tref. So yeah, they're just grabbing this So we're just calculating a ratio from yesterday's outside air temperature, comparing it today. And this will output an extra little minute kicker. Let's see, so where are we at here? So this will be an extra little, kind of tempting. Maybe I'll just blast this away. Heating ratio, cooling ratio. So compute the ratio of heating. So we're just pumping out some ratios. That makes sense. Pretty easy stuff. So they are saying that at 32 degrees, we would have to run the equipment 24/7. I have personally never seen that before. If they wanted to say, maybe in like Florida in the United States where it's very warm all year round, and 32 degrees is bad, but 32 degrees up in Wisconsin or Minnesota, close to Canada, is honestly not that bad. It's pretty warm. So I would adjust that to probably your climate. So they're saying that previous outside air temperature was 20 the day before in the morning when the optimal start algorithm ran, and the current outside air temperature is 20 or 15. So it's slightly different, a drop, and even warmer here. So these are our ratios that were computed. Why is a ratio greater than 1 when today is colder than... Why is a ratio greater than 1 today when today is colder than yesterday? I don't believe I saw this ratio greater than 1. Seems a little bit odd. Cooling ratio. Maybe it's because like we're below our maximum value. So I bet if I put this to 0, because Wisconsin, I would say we could run the equipment all the time if it's like minus 10 degrees F in Wisconsin. Yeah, sure, that's pretty cold. Not very out of the ordinary, but I would say like this is more common than this in degrees Fahrenheit in Wisconsin, but let's see what the ratio would be here. Okay, so now we're above our ratio. I think this question is kind of... I'm just going to skip that question. How would you pick temperature reference for your climate? So we talked about that earlier. What happens if today's outside air temperature equals the ref? Ooh, okay. So if today's outside air temperature equals the reference, division by 0. Haha. It's a 0 for the reference. So there wouldn't be any... I have to think about that now. So like there wouldn't be any... I think eventually we'll get into some parameters that are tuning themselves, like variables for alpha A and alpha B, and that if your temperature equals your temperature reference, then it just won't add anything or subtract anything. it would be exactly like model 0. Okay, so maybe we could blast through that. Day 17 multiplies base warm-up time by the ratio, which we've talked about, and time adjusted. If today is colder, yes. So mini example. I think this is exactly what we just talked about. For heating mode, T references that. Outside air temperature is this. Compute the ratio. I think this is the exact same code base. Why does a ratio blow up as outside air current approaches Tref? I think this just goes into what we've been talking about, is like you can't divide by 0. Why does the ratio blow up as outside air current approaches Tref? Well, let's try it. Wow, the ratio really does blow up. How the hell does it do that? So if our base, T base, so I think this is, this would be units of minutes. This is just temp and degree F. That's a good question. Why does this value here blow up as it reaches closer to Tref? I guess it just really makes the ratio go. Which makes no sense. I guess it's just that worst case scenario. As the current outside air temperature reaches that worst case scenario, that really makes your ratio go bonkers, I guess. Interesting. Would be kind of slightly interesting to ask AI about that. So here we are. Model 2 first computes the base rate, alpha A and alpha 2. I wonder if this would be a good place to stop, because then we can get into more tomorrow, calculating these tuning parameters. So, which is just the ratio. This is just another way of saying it was the maybe this would be a good place to stop. But so on day 17, I was kind of curious to ask, let's see if we can get into AI. Let's see, where were we? So we could say on the for the the question of why does the ratio blow up? Is it because the why does the ratio blow up as the outside air current? Is it because the outside air temperature is the Tref, which is the maximum outside air temp parameters, i.e. the 100 degrees C, or what were those numbers? I think those numbers were, they were our maximum values. They were these guys. Whoops, sorry. I.e. the, sorry. Or this. The worst case scenarios in terms of outside air temp, like the HVAC design day references for running HVAC 24/7. That is what explodes the ratios. So upload some context to you. Let's see, so we're on day 17. So maybe I'll just upload a couple of these guys. Good old ChatGPT. I think this might be a good day to stop, just because getting onto day 18. Yeah, maybe we can just put a little bit more time into thinking, computing the ratios and then doing like the alpha A, alpha B parameters. But this is cool. This is why is alpha A2 essentially the same as your linear rate in model 0, which is exactly what we've been talking about. So it is essentially model 0 with a little bit of an adder for outside air temperature determined by the ratio. Sometimes I notice ChatGPT just goes really slow. Curious if anyone else uses ChatGPT or notices this, or it's my internet connection. But I think sometimes it's just like the large language model services just get bogged down. Okay, come on. Maybe this will just be a good place to stop, and we can actually reconvene on this topic tomorrow. Ooh, I got it. Yes. Okay. Yeah, you've got it just needs a little sharpening. Go figure. The formula and where the blow up comes from. The ratio, adjusted. Tref references the outside air temperature. Yeah, so these are like our design day parameters. Previous outside air temperature, current T base is the runtime learned from yesterday. So that's our minutes calculations that were the danger zone denominator. So it's the denominator in the here is T reference minus the outside air current. T reference So if outside air current gets close to T reference, then outside air minus that is close to 0. So the ratio, something finite, something very small, is a huge number, which I guess makes sense. The ratio explodes because you're dividing a number, the T reference minus outside air current, that is approaching 0. How it ties to design day, worst case scenario, your mental model is right. Choosing boundary. So scale yesterday's runtime by how far yesterday was in the reference, from the reference, and how far today is from the reference. So when today's outside air temperature is very close to that reference, you're saying today is almost at my design day. The model weather correction is trying to extrapolate using the time difference between a reference, which is why the ratio goes nuts. You're outside of your comfortable numerical range of that little linearized correction. So cool. I think that makes sense to me. It's interesting though, like how boundaries is put on that and tuning. So I'm really curious to see how this model does. So I think that's all for today, guys. Come back tomorrow and we can see day 18.